So this is DIFUZE, Android kernel driver fuzzing. My name is Jake Karina. I am a recent graduate of the master's program at University of California at Santa Barbara, and I'm on Team Shellfish.
And I'm Chris Sauls. I'm currently a PhD student at UC Santa Barbara and also on the Team Shellfish.
All right. So this is the first talk I've ever given, so if I seem like incredibly nervous or anything, it's just because I am. So before I actually talk about DIFUZE, our system, I'm going to go through actually a decent amount of background information because I want everybody to understand that the problem DIFUZE is trying to solve. For some of you, this may be already known. If so, I apologize. Just bear with me a bit in the beginning here. Okay, so hopefully you have at least some familiarity with the Linux kernel, but the general point here is that we have the separation between user space and kernel space being more privileged, and the interface between the two is system calls. The kernel takes care of a lot of different stuff for us, things like process management, memory management, file systems, device control, etc. So for the purposes of this talk, we're going to be focusing on device control. Another thing to note is that the Linux kernel is a monolithic architecture, which for our purposes just means things like device control, it has the same privilege level as like anything else running in the kernel, which obviously has security implications, as we'll see. So device handling is done in the kernel. And how does that happen? So it's controlled by things called device drivers, which are generally implemented as Linux kernel modules. And they have to have some interface that they export to userland, right? So if you have some userland program that wants to use like the microphone to record audio, it has to have some way to ask the driver like, hey, can you help me talk to the microphone? And as you might expect, this is the same as the standard interface, which we just said was system calls. And so how do you do that? So in Unix, we have this notion that like everything is a file, and the same holds true for devices. So it's kind of weird to think about, but to some degree, like the microphone is going to be modeled as a file on our system. It's a special device file on disk. So that's still kind of weird to think about because it's like, okay, now I have this special file on disk that's supposed to be like representing my microphone. How do I talk to it? So before we get into that, let's look just like generally at operations on files. How are they done? If you consider the case for like a quote unquote normal file, so if you do like touch foo on your command line, right, and it creates like some empty file, say we're talking about Linux, it's probably an ext4 file, right? Now, if you think about some common syscalls that you can use to then communicate with this file or operate on it, things like open, read, and write, how do those know that this file that you're dealing with is an ext4 file in particular, right? How does it handle that? So to handle that, we have a thing called this file operation structure, or FOPS, or FOPS for short. And as its name kind of implies, it's there to define like, okay, given a particular type of file, how do I handle the operations for that file? So keeping with our example, I just said an ext4 file. So here is the code in the Linux kernel for the ext4 file operation struct. So anytime you interact with this file, like if we go and call open on this foo file we've just created, it's actually going to go down here, like down to the second from the bottom. It's going to say, okay, I'm calling .open on this ext4 file, and it's going to route execution to ext4 file open. So that's a specific function to open ext4 files. And so that's how this is done. We'll see this is kind of similar, or exactly similar to how it's done for device files. So now that we understand like a normal file, let's go back and talk about device files. So as we said, device drivers are generally going to create some special file on disk to represent the physical device that they're driving. And how is this done? So I want to give you some intuition for like, okay, given like a registration function for a driver, how is it creating the file, and where is this file operation structure coming into play, right? So I'm going to briefly kind of walk you through some code here. This is the registration function for an ISP device, that's image signal processor. It's like a camera. This is a camera device on a MediaTek phone. I'm just going to point out and walk you through some of the relevant functions here. The first being alloc char_dev region. So what this function is doing is it's saying like, hey, I am creating a new character device. I need you to allocate me like a range of device numbers for my device. And it's going to place them in ISP dev no, that variable I have boxed there. And furthermore, this range that you allocate to me, I want you to associate it with this ISP dev name variable, which happens to be pound defined. It's just a string. It's camera-ISP. Okay, so next, now we've allocated our device region for a device. Now we're going to call cdev init. So it's initializing our device. And what's it initializing it with? An ISP file opper. That's the variable. It is of type file operations. So good. So now we have some familiarity there. We just talked about those. And I'll actually come back to this particular variable and show you what it looks like. But for now, let's finish our device registration with cdevice add. So we've allocated the range for a device. We've initialized it with a file operations structure. And now we want to add it to the system. And so after this point, the device is like live, you could say. And so if you go and you look in dev/dev, hopefully you can see that, and we grep for that name that was associated with our device range, we see a file there now, camera ISP. So great, excellent. And you can also notice actually on the far left in the file attributes, that little lowercase c is telling you, hey, this isn't a normal file. This is a character device, right? So that's how you know. Now, if we go and call open on this, where is this call going to get routed? Well, we saw it was initialized with this file operations struct. So let's take a look at that. And here it is. So one of the first things you may notice is it's a lot smaller than the ext4 file operations. That's fine. You don't have to define every single operation for your file. In fact, it may not make sense, right? So we said this is like a camera device. What does it mean if you're like writing to a camera? It may not make sense. However, open, we see, routes to ISP open. And another one here that maybe not everybody is familiar with is ioctl, or the field is called unlocked ioctl. So I will briefly introduce what that is. ioctl, or IOCTL, some people pronounce it that way, stands for input-output control. And it's basically just a system call to allow device operations that aren't well modeled as like a normal syscall. So what do I mean by that? So imagine you have some audio device, right? And maybe it makes sense that if you're reading from that device's special file, maybe you're reading in like data from the microphone. And maybe if you're writing to that file, maybe it's writing data out to the speakers. But what happens when you want to like change the sampling rate? There's not really a syscall for that, right? And this is where ioctl comes in. It's just kind of a catch-all for like any kind of feature or functionality that doesn't fit well for normal syscalls. So from what I've just said, one really important thing I want everybody to note is that we said these device drivers are modular by definition, right? They're Linux kernel modules more often than not. And this is very nice for vendors because you have these vendors that are adding all this hardware, and now they can add support for it themselves in software. On the other hand, we said due to the monolithic architecture that the code that these vendors are adding is essentially running at the same privilege level as like mainline kernel code, which is kind of very scary. There's a lot of security implications there, right? And this issue, or what I'm telling you is an issue, where is it especially prevalent? In Android, as it turns out. So Android is based on Linux. It's currently dominating the smartphone OS market. And why is it especially prevalent here? If you think about like your average modern smartphone, it probably has like a back camera, a front camera, NFC chip, Bluetooth chip, Wi-Fi chip, gyro sensors, touch screen, tons and tons of hardware. And what do you need to drive all that hardware? You need device drivers. So it's a big problem on like smartphones, and we're looking at Android in particular. And so maybe at this point you're saying, all right, fine, whatever. Are drivers, are they really an issue? So I say yes, they are, but you don't have to believe me. This is a slide taken from Jeffrey Vanderstoep of Android Security. And what he has here is he has all these bugs, all these Android kernel bugs collected from January 2014 to April 2016. And what he shows is that 85% of them are coming from vendor drivers. So yes, so drivers are very much a problem, vendor drivers. And maybe you're wondering, like, why? What's the big deal? Why are these vendor drivers, why are they so bad? Like, what's going on here? We saw that, I showed you the file operation structure. It seems to be a fairly, like, well-defined, clear interface. Like open, read, and write seem like they should be fairly straightforward. Is any one syscall in particular causing all these problems? And as it turns out, as again, a slide from Jeffrey Vanderstoep, yes. So with the same data set, he shows that 63% of these kernel bugs are being reached via ioctl. So ioctl is a huge problem here. So with this said, it's probably prudent. Let's go back and take a more in-depth look at ioctls, and let's get a sense of why they're causing so many problems. So this is the prototype for ioctl. It has 3 arguments. First one's an intfd, so this would be a file descriptor to the special device that you're talking to. Next one is command. So we said ioctl is like a catch-all, right? That's probably encompassing more than one functionality. The one I gave was like changing the sampling rate. Maybe another is like changing the speaker volume for your audio device. And so that's where command comes into play, is you say like, okay, I want to change the sampling rate, or I want to change the speaker volume. And then the third and final param there is param, and that then is the data relating to your command. So for example, maybe your command would be like, hey, change speaker volume, and your param would be like 7. Like I want the speaker volume to be set to 7. And actually, more often than not, I'll also say is that this param argument is generally a pointer to data, not just like an integer value. So I'm also going to show you an example of what an ioctl handler looks like, because they all follow roughly the same kind of format. So we're going to look again at our same device, our ISP file operations, and we can see here that ISP ioctl is the function for handling ioctls. And that looks like this. And again, this is a very, very common format that you see for ioctl handlers. You have some big switch statement on the command, and then different cases for the different functionality you're offering. So here we see like ISP read register, ISP write register, and ISP wait IRQ. And also, I've pointed out with arrows what's happening in each of these cases. It's calling copy from user. So very, very briefly, if you're not familiar, copy from user looks like this. It's just a function to copy user from user land into kernel land, so that the kernel can like operate on it, right? And what this is telling us is that, yeah, param is indeed, it's expecting it to be a pointer to some data type, right? Some struct type, actually, if you can see. And another thing to note is that depending on the case it's dealing with, whatever command you're giving it, it changes. So for the first two, ISP read register and ISP write register, it's expecting a struct of type ISP reg IO struct. But then for the third one down here, ISP wait IRQ, well, now it's expecting that you should have given it a pointer to an ISP wait IRQ struct, okay? And so hopefully you can kind of see where the problems are now. The first being ioctl is a lot more functionality than just read or write. It has to encompass like anything that doesn't fit anywhere else. So it's generally a lot. The other issue is you're dealing with userland data, which is always risky, and it's in the form of like some complex struct. Okay, so these two things combined, it's like a recipe for disaster. So this is why ioctls present such an issue. And so now that I've hopefully convinced you that ioctls are an issue, what are some solutions? So I've kind of split it up into 2 here. The first would be static analysis. This would be like a code checker. The problem with this is, well, first of all, there's not a lot of good ones out there. But even the good ones, they tend to give you like a ton of false positives. All right, and you don't know. You have to go through every single warning and be like, is this real? Is this reachable? I don't know. And we don't want to do that. We're very lazy. That's a huge amount of work. I don't want anything to do with it. So the other alternative then is dynamic analysis. An example of which would be fuzzing. And if you can't guess from the title of our talk, that's what we went with, fuzzing. So okay, fuzzing very briefly. The general idea is you send like random data, random input into a program, and you hope you trigger a bug. And the really nice thing about fuzzing is you're guaranteed to find real bugs. Because if you're fuzzing a program, right, and it crashes, okay, obviously there's a bug there somewhere. And what's more is that depending on what you're fuzzing and like what program you're using to fuzz it, more often than not, you're also going to have like a POC to go with it. Or you're going to have like steps to reproduce the problem that you just saw or just triggered, which is very, very nice. Okay, so how is fuzzing then generally applied to the kernel? So in general, what you do is you can make a model of each syscall. So you say like, okay, the read syscall, it takes 3 arguments. The first is an integer. The second is like a pointer to some buffer. And the third is another integer. And then you go, and then you fuzz it, right? And hopefully you can see that this is very, very hard for ioctls. Because first of all, you don't even know like what's the device name. Like you have to go and hunt down like where are these special files? What are they called? What's the path to them? Furthermore, the command values for one device are certainly not going to be the command values for another device. They're going to be totally different. And third of all, even if you're focusing on just one specific device, as we saw, depending on which command you give it, the last argument, param, that's going to change. It's going to be expecting different types of data depending on the command. So all this together, it makes it super, super hard to make a model for ioctl. And then as a result of this, when kernel fuzzing, ioctls often get neglected because there is this huge amount of manual effort. And another thing to note is even with the recovered interface, even if you have all this information, some of these input parameters that it's expecting are like pointers to hugely complex structures, right? They may have substructs or pointers to other structs, and to instantiate something like this, it's not exactly trivial. So even at that point, it's still challenging. So with that said, now I'll introduce our tool, DIFUZE, that attempts to solve this problem automatically, so we don't have to do all this manual analysis. DIFUZE kind of like nominally stands for, it's like driver interface fuzzing, but then defuzz sounded kind of stupid, so we put an E on the end, and it's DIFUZE. So this is the general pipeline of our system. You give it kernel source code. It does some interface recovery step, so it retrieves all the information we just talked about. It's going to output that in some XML specification. Then from that, structure generation takes it. It says, okay, I have all this information about the parameters and the command values. I'm going to like make instances of these arguments. That is output as like a fuzz unit, and then that is sent to the on-device execution, where it is executed. And hopefully at the end, you get out crashes. That's what we like to see. So I'm going to walk you through every step of this right now. So starting with interface recovery. The first part of interface recovery is build system instrumentation. So the majority of our analyses use LLVM. What this means for us is that we want LLVM bitcode. Okay? This is a slight problem because the Linux kernel uses GCC to compile. And there's actually an ongoing project to just be able to compile the Linux kernel with Clang. Luckily for us, the issues that they're having, they come into play like very late in the compilation process. And it's actually fine we can get to the stage where we can emit LLVM bitcode, that's fine, which is very nice for us. So how we do this is we build the kernel with the provided make file, and we just like give it the verbose option. Be like, hey, tell us everything that you're doing. And from here, it's going to output like every GCC command it's using to build the kernel, and we save this to a file. So after this, we just have a script that runs through all these commands, and it just transforms like the valid GCC commands into Clang commands to emit bitcode. All right, and so now we have all this bitcode. And then finally, we try and link bitcode files together such that we don't have like a million bitcode files. We have like some semblance of like a pseudo object file for each device, just to make analysis easier. So now we have our bitcode. Next, we want to find all these ioctl handlers, because those are the functions we're interested in. So before we can actually find the handlers themselves, we have to find the definitions of all these operation structures. So the one I talked about earlier was a file operation structure. Turns out there's more than that. There's like watchdog operations, alarm operations, etc. There's a whole bunch of them. We have a list of these. And this part's kind of ghetto, but we just grep for definitions, the definitions of these structures in the includes. And then what we're going to do is where it's defined in like the relevant header file, we're going to use C to XML. C to XML is a tool that's part of Sparse. It was actually written by Linus Torvalds. And as the name suggests, it converts C code into XML. And the reason we're doing this is because we want to recover the unlocked ioctl field for the structure. So we want to be able to say like, okay, for this particular kernel, the file operation structure at offset 8 is where the unlocked ioctl field is. Okay. So once we find all these offsets, we store them away, and we can start some real analysis. Right, okay, so ioctl handler recovery. So now we can run the analysis. We start running some analysis on the actual driver bitcode files. And we're going to search for all uses of our operation structures that we've just talked about. And specifically what we're going to look for is assignments at those offsets we've just recovered. So if we said like, oh, the unlocked ioctl field is at offset 8, and then we see in the code an assignment at that offset, okay, well, whatever is being assigned there is the handler, the ioctl handler. So an example of that would be like this. So again, this is our ISP file operation structure. So here you see the unlocked ioctl field. And look at that. Okay, it's being assigned ISP ioctl. So we see this in the bitcode and we say, great, okay, so for this device, for this driver, that's our ioctl handler. So we can grab all of them this way. Okay, this is finding the device name, this step. So none of this does us any good if we don't know what the special device file is called. So for our example was camera ISP. So to be totally honest, the analysis we do for this is pretty boring, and I'm going to skip it. I'm more than happy to talk about it at the end if somebody's interested. But what it boils down to is if it's registered with a static name, like in the example we saw, we can recover that. So we would be able to find like camera ISP, great, it's static, excellent. Unfortunately, you're going to have stuff like this, where it's a dynamic name. So here, the name, it's like sprintfing into the name, and it's like getting the name, it's like indexing into some global table. We don't know what this is. And unfortunately, we're going to have to fall back to manual analysis. Or you can just set an option to be like, OK, skip anything that we can't find the name for. OK, so the next big thing is now we have all these ioctl handler functions. OK, well, we want to know what do we send them, right? We need to know the command values and the types that go with those command values. So this analysis is done in tandem. We find both of these things together. What we're going to do is, because we've recovered these handlers, we run our LLVM analysis on the handler function, the bitcode for it. And we know our arguments of interest, right? So we know that our second argument is the command value, and the third argument is param. So this is very nice, because all we have to do is search for any kind of equality comparison on our command value. And if we see it, we keep track of that constraint for the given path, like where that equality comparison applies. And while we're on that path, we're then going to look for any uses of copy from user that's using our third argument, that's using param. And if we see this, we're going to look at the first argument to copy from user. That's where it's copying data into. And we say, OK, well, if we know the type of what it's copying it into, that's obviously what it's expecting param to point to, like a type of that data. And additionally, this doesn't necessarily happen at the top level of an ioctl handler function. And so we're going to follow any function that gets past param and or command. And so I know that was a decent amount of text. So I have an example here for you. Here's our good friend, the ISP ioctl handler. And what we're going to do is, OK, here's our switch, like we're used to. And here's a case. All right, cases, they boil down to equality comparisons, right? This is going to be like, in the assembly, it's going to like, oh, like, is, whatever, this register, is it this value? So we keep track of that, we make note of it, and we continue on this path. OK, here we see a function call. And what's going into this function call? Param. OK, well, we said that's one of our arguments of interest, so we're going to follow the function. So we come down here to ISP buff control func, and what do we see in that? We see a copy from user. And what's it using in copy from user? Param, again, our argument of interest. So we say, great, OK, let's look at the first argument to this. Where is it copying it into? RT buff control. What is the type of that variable? It's an ISP buffer control struct. So now we have this pairing, we have this match. We say, OK, if we give this handler a command value of ISP buffer control, we should also expect to give it param pointing to a type of ISP buffer control struct. And now we have these matches. This is very nice. So we're almost done. The last step is that, OK, just because we know the type that we have to give it doesn't necessarily mean we know what that type looks like, right? Because we need to, if we're going to instantiate these, we have to know what the type actually looks like. So the nice thing is we have all these GCC build commands from our first step, where we used the makefile and we just said, hey, be verbose. And we know what file we're looking at. We know that for this given bitcode file we're looking at, it's like it has this other relevant C file. And so all we have to do is go and find the GCC command that was used to build the C file originally. And then from there, we throw on the -E option to the original build command that's going to invoke the C preprocessor, which means for us, if somewhere in that C file it used this struct, it has to, like, after the preprocessor, after it resolves all the dependencies and stuff, the definition of that structure should be in the preprocess file somewhere, and anything that it relies on. So from there, we're going to run our good friend C to XML on the file. We're going to get some equally massive XML file. And then we're going to run a series of Python passes to extract the struct and any struct dependencies. Like I said, maybe the struct has pointers to other types of structs inside of it. If so, we need to know the definitions of those as well. And it's also going to do things like account for padding, recover enum values, etc. So just to give you a bit of like a visualization for what this looks like, I'm sure this is unreadable. This is what C to XML gives you. So it's not very useful like for human analysis. Like if you're just looking at it, it's not helpful. But it does have a ton of information in it. After we run our Python passes on this, we distill it into something that looks like this. So much more digestible, much more readable. This is a data model for a particular type of struct. It looks very similar to Peach, if some of you are familiar. OK, so that was a whole lot. So a quick summary of what I've just discussed. We started with the kernel source code. From there, we compiled to LLVM bitcode. From the bitcode, we recovered device names and the ioctl handlers. From the handlers, we got the command values and the argument types. And then from the types, we went and we found, OK, what do those types actually look like? What are their definitions? And so those last three things, the device names, commands, and type definitions, are going to be pushed into some XML specification describing it as the interface.
Awesome. So after all those steps which Jake has described, we are now fully interface aware. We know what the device file name is, so we know where in /dev, what /dev file we need to open. We know what command IDs the ioctl accepts, so what numbers to pass it. And we even know for each of those command IDs what the argument type is, what structure it's expecting is. And so the next part of this fuzzing process is we have to generate actual instances of these structures so that we can begin to fuzz the device and exercise its behavior. And this all resides in the structure generation component of DIFUZE. And so the structure generation component actually still happens on the computer, on the analysis host as we call it, not on the Android phone itself. The structure generation component will output fuzz units as we call them, which will be a single invocation of an ioctl. All right, so let's think about structure generation. If we have a struct type, one of those buffer control structs or whatever, how are we going to generate an actual instance of it? So at first it seems pretty simple. Each of these, the struct will have a bunch of fields, integers, longs, characters, etc. And we should just generate each of those as we go. Of course, it's not quite so simple. There are some more complex cases. If we consider what if there's a pointer to another structure? What if there's a union or enums? We need to handle these as well. So let's walk through a simple example of how this works. We have this structure, ISP buffer control struct, and we're going to go through each field one at a time and generate the elements it needed. So we're first going to handle this field called control, which is just an enum. So that means when we generate the structure, we should pick maybe one of these enum values or maybe something that's not an enum to try to trigger an out of bounds. And we're going to go on. The next one is also an enum. So we're going to grab its definition as well. And we go on, and this one now is a pointer to another structure. So we have to be a little bit more careful here. So we have to actually generate this structure as well. So we're going to recursively handle each structure we see. So we'll see this structure, and then we'll go through its fields one at a time, handling them, creating them. And of course, these structures can be complex and have structures within them or pointers to other structures as well. And after we've generated the second structure, we need to point this pointer we've in the first one to it just to have the mappings correct. And we'll go through and keep doing this for every element of our structure until it's generated. Now, the other component of this is, of course, what values do we pick for these elements in the structures? And we can be pretty smart here. So we know that the type of every single one of these elements. We know if something's an integer, a long. We know if it's an enum. So for enums, we can try to pick values that are correct or incorrect. We can intelligently pick integers that might trigger, say, a buffer overflow boundary or an off by one, so maybe closer to a power of 2. For character arrays or whatever, we can try to create both long and short arrays to maybe trigger both buffer overflows and valid functionality. And so for each data type, we have a few strategies of how we randomly pick values for it. And this all makes up the structure generation component of DIFUZE. And the structure generation component, as I said earlier, is going to output these fuzz units, which will go to the on-device execution step to be executed. All right, so the name of the fuzzer itself is Mango Fuzz. It's based off Peach, which is where it gets its name. It's a fairly simple fuzzer and kind of dumb. It's written in Python, can only handle ioctls, and it consumes these XML spec files, which we create during the interface extraction step. The XML spec files contain all of the interface information which we need to do a single fuzzing iteration. These XML spec files contain the device path, all of the command IDs, and for each of the command IDs, what the argument types are, and for each of those argument types, their definitions, so we can actually generate those structures. And Mango Fuzz, on the analysis host component, will generate binary blobs and some mappings between the binary blobs. So if there's a pointer from one binary blob to the next, it'll have a mapping tell you which pointer it needs to fix up on the device itself. And an example of this XML spec, which I mentioned, is shown here. As you can see, it shows the device name, the ioctl ID, or the command number, as well as the target struct expected by that ioctl. And for that structure, it will have the structure elements, the fields needed down below in the data model. And if that structure references any other structures, we'll include those as other data models as well. And then, so MangoFuzz, on the computer part, the analysis part, host part, will generate the fuzz units to be sent to the device for the on-device execution. And that happens on the device. That's where we need to actually call ioctl to trigger the functionality. And so we simply connect the computer to the device through ADB, the Android debug bridge, where it'll run a program called the executor. And the executor will open a port and listen for data. As it receives data, it'll map it into memory. Just call malloc for the right size, copy the binary data in there. And then as needed, it will fix up the pointers so that if one binary blob references another struct, those happen correctly. And then it just simply opens the device file, calls ioctl, and hopefully triggers some good functionality and maybe triggers some bugs. All right, so when we get to actual fuzzing, it's pretty simple to look for bugs. So on Android, if you crash the kernel, the device will reboot, and you'll hear a nice beep or something as it's rebooting, letting you know that you might have found something good. Then the kernel backtrace or oops is saved in sysfspstore console RAM oops. And you can look there to use that for triaging. We also save the whole sequence of ioctls, and that can be trimmed down to try to triage the crashes a little bit better, because if you've done any triaging, it can be pretty annoying just to look at the actual inputs. So the combination of the RAM oops and the backtrace of ioctls, which we can filter down, help a lot. And to test our system, we ran it on 7 phones from 5 major manufacturers, including Google, HTC, Huawei, Samsung, and Sony. And across these, we think we covered 4 different chipsets, and this includes a wide range of devices and drivers, and should give us a large number of ioctl handlers to test. In total, we ended up finding 789 ioctl handlers across these 7 devices. And this resulted, and for these 789 handlers, we were able to identify the device names for only 469, which is like 60% of them. I think this is the worst performing part of our system, the part that maybe needs the most manual analysis or future work to make good. But still, 60% of these is a lot of the handlers, and most of the misses comes from mainline kernel drivers, not from the vendor-specific ones. For example, on MediaTek, we specifically found around 90% of the device names for the vendor-specific drivers there. So, and those ones are often the ones on Android that you're looking for bugs, or the ones maybe more likely to be buggy. And so we're getting very good coverage there. For type and command ID recovery, we do better. So we found across those 780 command or ioctl handlers, we found a total of 3,565 command IDs. And for slightly under 50% of them, we found that the user argument is not an input pointer, meaning it's just used as a C-type integer or long, and not as an input pointer, or it might be used as an output pointer, copying the result to you. But for the rest, the remaining 53%, we found these were using an input pointer, so it was copying data from a structure or from a user data type to the kernel and using it. And we did a small random sample to check the accuracy of our tool. We picked 5 ioctls for each phone, which is a total of 35 handlers. And we found that we were accurate for both the command ID and the type on 90% of those. Okay, to do the actual fuzzing evaluation, we picked 4 different variants, which included various levels of device information, or the interface information, which we've extracted. And we ran this. First, we used syscaller. Syscaller is a state-of-the-art Linux kernel fuzzer built by a very good team at Google. And if you give syscaller the definition for a syscall or set of syscalls and how to call them correctly, it can fuzz them very well. And so we were able to interface with it. And so we gave syscaller just the device path, which would just be the device name and the ioctl numbers, and then the full device info, which would be the device name, ioctl numbers, and the structures associated with it. And we also ran our fuzzer MangoFuzz with the full device, the full interface info. And when we were fuzzing, we found quite a few bugs, actually. We hit 36 total unique crashes across these 7 devices. You can see here which for each of the different tests and each of the 7 phones what we found. The best performing one was syscaller with the full information extracted by DIFUZE, kind of as expected, which got 34 crashes. However, DIFUZE with MangoFuzz, our much simpler fuzzer, that of course only handles ioctls and is significantly slower, still was able to find 30 crashes. And this to us really shows how important the interface information was, because just using this in a kind of hacky and dumb way, our fuzzer was able to still get 30 crashes and not that many less than a state-of-the-art tool using the same info. With just the path, you weren't able to get many crashes, just 3. But when we gave it the path plus the ioctl command numbers, we were able to get 22 crashes, which is a bit more, but still, you need the full structure information to get the remaining 50% increase, the 34 crashes. And those ones with the structure info, those will probably be the deeper and more useful bugs than the ones where you just give it the device and the command numbers. Oh, and one more thing. Although, of course, some of these were like nullity references and not all exploitable. For example, on the Pixel, we have 5 crashes here. 2 of these were exploitable. One of them we wrote an exploit which could escalate from audio permissions to kernel. And we've submitted both these to Google. Unfortunately, they're not public yet, so I can't talk about those ones specifically. But I have some other fun bugs I'm going to talk about in these next few slides. All right, so this first one on MediaTek, we found an out-of-bounds write. And this one's kind of fun to me because it ends up being the developers put a curly brace in kind of the wrong location. So let's look at what happened. In the beginning, they initialized this free ID to -1. Now they're going to loop through this for loop just following this statement and try to find a new free ID. And if they can't, free ID will still be -1. And so down here, there's this if statement that handles free ID -1. But this else statement is where they wanted to fix up the free ID if it was still -1. And somehow they messed this up, and of course this will never happen because free ID was -1. It'll go in the if statement, not the else statement. So you'll get down here, free ID is still -1, and you end up with an out-of-bounds write to index -1. And this is actually a pretty useful write. It overwrites some very useful pointers, and we were able to make an exploit that escalated from any app on this phone to kernel permissions. All right, and then this next bug, I really like this one because it's actually a bug in the bug function itself. So when we were fuzzing, we saw this in the last K message, unable to handle kernel paging requests at virtual address 0000 dead, DEAD. Now, that looks like a cert failure or something, and of course it was. In the bug handler, they wrote their own bug handler that just tried writing to OXDead to kill the kernel. And of course, this is a mistake because you can just mmap at OXD000, and then the kernel will try writing there, and it'll just work because there's no, or on most Android phones, there's no permission control preventing the kernel from writing to user land. And so if you mmap there ahead of time, you can just bypass these bug or cert macros. It's used for all of the cert macros in the kernel. And so all certs became worthless, and you could skip them and trigger some memory corruption. And then a last bug we found, one time while we were fuzzing one device, suddenly the fuzz reported couldn't find it. We unplugged the device, plug it back in as usual to try to reset it. Still doesn't work. Unplug, turn the device off, turn it back on, plug it in, still can't find it. And we look more closely, and the serial number has changed to that random string there. So the device we were fuzzing apparently let you write to NVRAM, which is non-volatile memory, and you should never be able to write to NVRAM as any normal or user or even root on the phone. And so I think that also was due to an out-of-bounds index as well, that there was some spot they actually intended you to write in there. But either way, we ended up overwriting the serial number. You could change all sorts of stuff, including like the IMEI and other important information, and permanently damage the device. All right, some of the future work that still needs to happen to make this, to continue finding bugs with this project. On most of these phones, it's very hard to compile with KSAN and K-coverage. KSAN is very useful because it will report crashes much that sometimes you won't, or will report bugs that sometimes might not result in crashes immediately. So like if there's a use after free at all, it'll detect it and report it to you, and you don't have to wait for that use after free to be using a pointer or something else that you control. K coverage, syscaller can use the coverage info to try to perform better fuzzing, and I guess that's one of its really strong points, to perform mutational fuzzing by knowing what functionality is triggered. And again, it's hard to compile this into most phones. I think the only one we've been able to do with KSAN and KCov is the Pixel. And of course, you can run this fuzzing on more phones. You can run on standard Linux drivers and other devices. And in conclusion, driver fuzzing can yield a lot of bugs, as we've shown. But one important aspect is that you need to model the interface correctly. If you don't model the interface correctly, you're going to miss out on most of the functionality, and you won't be able to hit lots of these bugs. But fortunately, DIFUZE, our tool, automatically extracts this info for you and can be used to make this fuzzing easy. It's available online on GitHub, on github.com/ucsbseclab/diffuse. You can go try it out and fuzz things yourself. Awesome. Thanks for coming to talk, and we'll now take questions from the audience. Yeah, they're bringing them up.
Hello, Stefan from Austria. Quick question on the Pixel. You were able to compile it with coverage information. I'd be very interested on what kind of code coverage level you were able to reach, because drivers, in my experience, are stateful rather than stateless. So some code paths are only triggered if you have triggered some other code path before. So I would be interested in your results in that area.
I don't think we have any coverage.
Yeah, we actually didn't even, we were getting so many crashes with just KSAN, we didn't even attempt with KCov. It was a bit overwhelming for us.
We still have more crashes to look into at this point. I don't think we've ever looked into what sort of coverage.
Yeah.
Mostly been find crash, check it. Often we patch some of the nullity references or whatever and keep looking at more crashes. Right. And of course, there's been a lot of phones.
Yeah, sorry.
Yeah.
Does any of your work assume things like the device has been rooted, or you have root access to do some of these things?
Yeah.
Yeah, it does. So it doesn't have to be, but it's the most useful. You'll get the most coverage if you root, because even though from like an exploitation perspective, maybe it's not as interesting that you need to have like audio permissions as a starting permission, but I mean that's still like a valid bug.
Yeah.
And so we run as root so that we can touch any driver we want.
Then maybe a suggestion, as a follow-up suggestion for the part that you said that is probably the one that you need to work a bit more. Maybe you can just list the dev files and then try to do an IOP tool with a given number on them and see what happens.
Okay, yeah, sure.
Yeah.
That makes sense.
Hi. Did you run any benchmarks about times and minutes, hours took for both the static phase and also the fuzzy phase?
Yeah, we definitely did. I don't remember them off the top of my head.
The static phase doesn't take that long, right?
Well, I mean, it depends on like what kind of machine you're running it on, of course.
We run a 40-core machine, takes like what, under an hour or 2 hours?
Yeah, it'll vary depending on how many like ioctl handlers it finds and stuff. If you look, so this is actually a CCS paper as well, so we have all the timing information in the paper itself. I don't know it off the top of my head, I'm sorry.
Next question in the back.
Hi, my name's Bernie Goodhart. So you talked about ioctls and how you've parsed them to get all the parameters and so on, and using user copy to copy in. But you can't use the ioctl until you've opened the devices, and in order to open them, you need to specify the correct arg, vargc, and so on. So what I'm saying is do you parse the open as well in order to?
Yeah. So some of the interface information we have is like the path to the device. So yeah, we can open it. I don't know, maybe I've misunderstood the question.
No, I'm just saying, like, you know, once you've opened up a device and you can then get to the ioctl, yeah? You can't get to the ioctl until you've opened up the device.
Right.
But in order to open up the device, it's not just as simple as saying open/dev whatever.
Why?
Because a lot of devices will refuse to open unless they've got the full argument structure.
They're already. Maybe we should talk after, because as far as I understand, it should be fully the device has already initialized everything and.
Okay, I'll talk to you offline. I'll talk to you. The other, sorry, I've got one other question.
Yeah.
It seems to me that the magic in this is in the Python build that you. Sorry, no, in the Clang build, and what engine you use there to decipher all the ioctl information and so on. But you're using the source code of the entire mainland tree there, or are you just of specific device drivers?
The whole tree.
The whole tree?
Yeah.
So if where I'm getting a bit confused, and maybe I missed the point, and we should probably talk offline, I don't know if anybody else is interested, but if you've got the entire source code tree, why don't you just parse the actual code proper?
It's actually a lot harder than you would think, parsing the C code as opposed to...
Well, you're just using the preprocessors now?
So you just use the C preprocessor and then generate the bit code. And then it's pretty easy to parse it inside LLVM, and I guess you could parse it in source code. I don't know if that gives you much of an advantage over doing LLVM.
Yeah, I've done this before, long time ago on Unix systems, so I'll talk to you anyway.
Okay.
Cheers, thanks.
Yeah, sure.
What's the next question?
Okay. Actually, I think I missed something, but in the case of the structures that has a pointer to another structure, have you done analysis for, using a kind of a recursively to analyze the structure, right?
Yeah.
Yeah, and how deep did you go through the structures?
Yeah, Jake. So we limit recursion. I think.
If it's like a recursive field, I think we go one level deep, and then we just set the next recursive field to be null.
Sorry, pardon?
So if it's a recursive structure, is that what you're asking about?
Yeah, right. In the case of the structure has a pointer to another structure.
Yeah. Oh, okay.
Sometimes from my experience, some structure has a many levels of a recursive pointer to another structure.
Yeah.
So did you always go straight till the end of the recursive structure, or have some limitation to recursive depth?
We go until it ends unless it loops back around. So if you get a pointer to if you have like a next pointer and it's a pointer to the same structure, that could go forever. And so in that case, in our fuzzer, we limit it. I'm sure syscalr might handle it a little bit differently and try different levels, but we just limit it to, if there's a recursive one where it's the exact same structure is reached again in this loop, we limit it and do a null structure there.
Thank you. Next question. Sure you don't have any more questions?
I have a second one.
So since you're already compiling the code, have you thought about using this essentially as static code analysis and feeding your fuzzer? You said you have some edge cases for integer, off by ones, and so on. Feeding it essentially the code paths that are triggered by some specific by some inputs. So if you look in there, if this byte is set to this, then do this and that.
Take it. We haven't really done anything there. I could definitely see ways you could use the actual, like instrument it or watch which paths are covered here to do further, to try to trigger the specific ones or maybe edge cases you're missing. And giving syscalr kcov information can also hit some of these paths that you're missing.
Okay, thank you.
One more thing to note. There's like a brother paper to this called Dr. Checker, which takes all this LLVM bit code and it does just do like just static analysis on it actually. So that, yeah.
Have you heard of a Python packet called ctypesgen that generates Python structures from C structures? Because it seems that it does what you are doing.
No, I have not heard of that.
Okay.
That sounds convenient.
Can look at it.
Yes.
Next question.
So this is lovely work. About 10 years ago, I worked on a bindings generator project for dynamically generating interface code between C and C++ across a number of different runtimes. It seems like the big problem that you have here is the analysis of the Linux kernel source. And one thing found to provide a lot of mileage was actually using the CDT project from Eclipse, because it gives you full abstract syntax trees for every bit of C code that it sees. And you can search by structures. So those IRQL calls, the structures, you'll actually just be able to pull out in about 5 minutes. And it'll give you full... Take a look at it. It might make your life a lot easier over Clang.
We'll take a look.
Yeah,
Thanks.
thank you.
No more questions?
Awesome. Well, thanks for coming to our talk.